Algebra 2 CST released. I'm going to do 4 problems here. All these 4 I'm going to do are going to deal with exponents and working with our exponent rules. Specifically, I'm looking at 58, 60, 61, and 62. We look at 58. Jeremy, Michael, Shannon, and Brenda each worked the same math problem at the chalkboard. Each student's work is shown below. Their teacher said that while 2 of them had the correct answer, only one of them had arrived at the correct conclusion using correct steps, meaning one of them got kind of lucky. So the first thing we have to decide then is the fact that, again, 2 of them got the right answer. It says, which is a completely correct solution? So we look at Jeremy's work. Start with x to the third. They all start with x to the third times x to the negative 7. Now he's thinking flip. I'm going to put that over 1. Flip this x to the negative 7 to the bottom. He's got the right idea. So we put that on the bottom. But when you flip that negative exponent to the bottom, it has to become positive. That is an incorrect step. So look at Shannon's work. Now it's the same idea. They put x to the 7th on the bottom. That did work out nicely. So x to the 3rd stayed on top. X to the 7th one on the bottom became positive. That is correct. And then when they simplified this, they've got 7 minus 3 is 4. When you're subtracting exponents with a fraction, the x to the 4 stayed on the bottom because you have 7 x's on the bottom, only 3 on top. You're going to keep them where you have more of them. So that is correct. Shannon is actually right, which means our answer is going to be C. Now, just to look at this, Michael's work, 3 on the top, negative 7 on the bottom. That is actually correct, x to the negative 4. But this negative 7 on the bottom should have been positive 7. Here, Brenda's work, x to the 3rd, x to the 7th, that's correct. But they just subtracted, they didn't keep the x on the bottom of the fraction, they put it on the top. Next one, switching to, is number 60. They ask us for the first incorrect step in simplifying all this madness. So we got x to the 2nd raised to the 3rd minus x to the 5th raised to the negative 1. The first step is they're taking this x to the step raised to the 3rd, making it x to the 6th. That is correct. The parentheses were multiplying exponents, so that is right. Then they made this negative 5 times negative 1. That is also correct. So this first step is fine. Second step, they took this x to the negative 5th and flipped it over to make it 1 over x to the positive 5th. That is correct. Third step, when they're subtracting, they just went ahead and put the x to the 5th on the top, which would be fine if you're multiplying. But since we're not multiplying, we're subtracting, you'd have to actually get a common denominator to subtract those. So step 3 is where they made the mistake, which means our answer for 60 is C. Someone's calling me. Our last 2 in this video will be 61 and 62. 61, you've probably seen before. We've had this on a few reviews. A certain radioactive element decays over time according to the equation y equals a times 1/2 to the t over 300, where a equals the number of grams present initially and t is the time of years. If 1,000 grams were present initially, to notice that key word, present initially, which means that's your a value, how many grams will remain after 900 years? So what we're looking for is, we're solving for y. T, 900 years would be t. T is your time in years. So what we're trying to figure out is 1,000 times 1/2 to the 900. I'm taking that t, substituting 900 to over 300. And it looks kind of crazy, but it's much easier than it looks. So we'll start with 1,000, 1/2. These cancel, zeros cancel, leaves us with 3. 1,000 times 1/2 to the 3rd power, 1/2 times 1/2 times 1/2 is 1/8. And then all we're doing really is dividing 8 into 1,000, which would give us 125. So for 61, we get 125 grams. 62 will be the last one for this video. Bacteria in a culture are growing exponentially with times, shown in the table below. On day 0, the initial amount is 100. Day 1 equals 200. Day 2 is 400. So which of the following equations expresses the number of bacteria Y present at any time t? What we're trying to find is, first, since we know it's exponential growth, we're trying to find the multiplier. The 0 gives us the initial value. Remember, what we're looking for is a times b to the x powered. That's the kind of pattern we want. Right away, we know it's not going to be a because of the addition. So no, we have to have a multiplier. And if you look at part C, it looks like there's a 2, that's probably the multiplier, but we don't have an initial value. It does not match this pattern. That's not going to be it either. So it's got to be one of these two. Now remember that we're multiplying by 2 each time. 100 times 2 is 200. Times 2 is 400. Times 2, the next one would be 800. They both have a multiplier of 2, so the only thing we have to decide is the initial value 100 or 200. And remember that for that number in front, for this initial value, you'll always look for the 0 amount. On day 0, that's the one we're concentrating on, which means our initial amount has to be 100. So our correct equation for 62 would be b. Y equals 100 times 2 to the t power.